Are you a musical person? Do you have perfect pitch? If I play this sound here, and then I play this sound, can you tell what the difference is? You probably noticed that the first sound was lower and the second sound was higher. If you have musical training, you may have recognized that the interval between the two notes was a major sixth. And if you have perfect pitch, you may recognize the notes as a C and an A. But what does pitch mean when it comes to sound? We know that sound travels in waves, and that those waves are characterized by their wavelengths, amplitudes, and other parameters. If the two tones I just played come from different sound waves, then what exactly about the waves is different between the two? In this lesson, we're going to explore the more familiar characteristics of sound, like pitch and volume. We'll talk about what these mean in terms of the sound waves we've learned about so far in this chapter. By the end, you'll have a deeper understanding of how sound works and maybe appreciate music a little bit more. Let's start by recalling a few things about sound waves. While sound can travel through all types of substances, we're going to use air as the medium in our examples here. A great way to visualize longitudinal waves in air is to think of the sound coming from a guitar string. When you pluck the string, it vibrates from side to side, pushing the surrounding air molecules in a periodic fashion. The compressions and rarefactions in the air comprise a longitudinal wave, which we detect as sound. If we could look at just one air particle, we would see it oscillating back and forth. Sometimes the particles move back and forth over a very large distance. Other times the particles oscillate just a little ways. The amount of oscillation in the particles of the medium is related to the amount of energy carried by the wave. Can you remember which of the 5 wave parameters describes a wave's energy? And by wave parameters, I mean the frequency, wavelength, period, speed, and amplitude. The one that describes a wave's energy is the amplitude. In a transverse wave, the amplitude can be seen as the height of the crest. But in a longitudinal wave, like sound, amplitude is a measure of how far the particles oscillate back and forth. In a high-energy wave, the amplitude is large because the particles oscillate over a large distance. A low-energy wave has low amplitude because the oscillations are small in size. So now we get the relationship between energy and amplitude, but how does that translate into what we hear as a sound wave? The energy in a sound wave has to travel over a certain area in a certain amount of time. We detect sounds as being louder when we're standing closer to the source and quieter when we're standing further away. The amount of energy we detect is known as the intensity. Intensity is measured in units of energy over the area and time. In other words, it's the amount of energy that is carried over a certain area in a certain amount of time. We describe different levels of intensity using the decibel scale, a logarithmic scale for measuring the intensity of sound waves. Normal conversation generally falls around 60 decibels. A whisper is more like 20 decibels, while a vacuum cleaner runs as loud as 80 decibels. You may be more familiar with decibels as a measure of volume. When talking about sound waves, the volume is the perception of loudness from the intensity of a sound wave. The higher the intensity of a sound, the louder it is perceived in our ears, and the higher the volume it has. Since intensity is a function of energy, and energy is related to amplitude, then we can make the conclusion that the volume of a sound is proportional to the amplitude of the sound wave. It was a little tough trying to visualize the amplitude of sound waves. Because sound is a longitudinal wave, we don't get the nice up and down wave shape that makes it so easy to see the parameters. We figured out a way to see the amplitude of sound, but what about the period and frequency? Is there a way to see the parameters that are related to time? Let's say a sound wave is traveling toward a microphone. The microphone picks up compressions and rarefactions as the wave passes by. When a compression hits the microphone, it receives a high amount of air pressure from the particles in that space. During a rarefaction, the air pressure is very low. Over time, the microphone experiences ups and downs in pressure, which we can illustrate as an up and down wave like this. It looks like a transverse wave, doesn't it? But it's really a plot of pressure over time, showing us the periods between successive compressions of the wave. If we take the reciprocal of the period, we can find the frequency. This sound wave has a frequency of 262 Hz. So what does it mean when we describe waves as having a certain hertz? Sure, we know it refers to the frequency of a wave. A wave of 262 Hz has 262 wave cycles passing by every second. A wave of 440 Hz has 440 cycles a second. But what does that mean for a sound wave? Can we hear the difference in frequencies between two sounds? Let's go back to those two sounds we heard in the beginning. The tone played here has a frequency of 262 Hz, and this tone here has a frequency of 440 Hz. The first one was middle C, and the second was the A above middle C, or concert A. In music, the pitch of a certain note is defined as the perception of frequency. Hearing musical pitch helps us to put different sounds in order from high to low frequency. High-pitched notes have a high frequency, while low-pitched notes have a low frequency. The difference in pitch between middle C and concert A is a difference of 178 Hz. Humans can typically hear sounds as low as 20 Hz and as high as 20,000 Hz. This range is known as the acoustic range of sound. Sounds above 20,000 Hz are considered ultrasound. Dogs, dolphins, and bats can hear sounds in the ultrasonic range. At the other end of the spectrum is the range of infrasound. These are sounds that are too low for us to hear, like the communication calls between whales and elephants. Obviously, we humans only play our music within the acoustic range of sound, between 20 and 20,000 Hz. When you're able to discern a difference between musical pitches, just know that what you really perceive is a difference in the sound wave's frequencies. Sound waves are longitudinal waves that require a medium in which to travel. The medium consists of particles that oscillate within a certain amplitude. The amplitude of a sound wave is a reflection of how much energy is carried, which contributes to the intensity of the sound. Intensity is measured in decibels and is perceived as sound volume. Thus, the volume is proportional to the amplitude of the sound wave. The frequency of a sound wave is perceived as pitch. Humans can detect pitches within the acoustic range of 20 to 20,000 Hz, but we can't detect ultrasound or infrasound. We can hear changes in frequencies of musical notes, which we describe as being changes in pitch. When we hear sounds, we describe them based on the pitches and volumes that we perceive. These entities are simply our perceptions of the frequencies and amplitudes of sound waves.